define complex function by using power series. Alright, so Z0, a fixed complex number. So it will be the center of a power series, Cn, a sequence of complex numbers. Okay, so you can see to define a power series is you have to give the center of the power series, so it's a fixed point, a fixed complex number, as well as a sequence of coefficients. So it's a sequence of complex numbers here. So these two data, all right, these two data give you power series. So now we define. Okay, so we define a complex function. Okay, f of z on the open disk B z0 is 0. Okay, as f of z defined to be the summation. So it's the sum of the series. Okay, and where one of the row is the insert of the square root of the nth root of the x value of the coefficient. And this function is well defined because we already shown that we have already shown that for any z in this open disk, the series sum converges absolutely. Okay, so you have a definite value. Okay, for this sum, for this series sum. Okay, and you see that the disk actually is a convex open set. It's simply connected. It has all you want as a geometric object in the convex plane. It's quite nice, right? Quite nice. Okay, and so okay, so this function is given, all right, by a power series. Now, function given by a power series has a nice property. First of all, so we are given a function by a power series. So okay. So rho is the ROC of the defining power series. Okay. Then f of z is analytical. Alright? So f of z is analytical in the open disk. B of z0, rho. And its derivative. And its derivative can be written, okay, as n Cn z minus z0 minus 1. Okay. also a power series, right? You can see it's related to the power series. Right, which is the same ROC. Okay, so that's the conclusion is very important that for any function defined by a power series, it is analytical. Okay, it's analytical. Okay, in defining disk, and its derivative can be written here, right? By a power series. And this power series became very simple, just by the derivative term by term, right? You can see that. Alright, so it's very important. The third thing is that this power series has the same ROC as the original one. Okay, that is not easy. I can't say that it's not easy to prove, but I just say that it's a little bit surprising, right? Okay. Okay, and the proof a little bit long. Okay, so I just skip the proof. So I want to give you applications. So by iteration, the complex function f of z given by a power series right. The complex function given by a power series is case derivative A, C. Okay? For all k and 1. And this case derivative can be written by right. So the case derivative here, which has the same ROC as f of z and 0. So this case derivative defined for every z in this open disk. So any function defined by power series is quite convenient, right? You can write down the case derivative, and you know its ROC is the same as the power series, defining power series. Okay, so now I state some consequences. In the textbook, it says continuity of the sum power series. Okay? If a complex function f of z is defined by a power series about the center is 0 with ROC equal to 0, then f of z is continuous on the disk. This is, of course, is true because we just come to hear that such a function is analytical, right? So it's differentiable, and the differentiability implies continuity. So this, of course, this is true. About uniqueness of a power series expansion, if a complex function, all right, f of z is given, all right, by a power series about a center is 0, then the given power series, all right, is unique. What? But look at here. If a function f of z is defined by a power series, so f of z is defined a power series. Now, actually, the power series can be recovered from the function. Remember, a power series is defined by the center as well as the sequence of coefficients, right? So we know already the center, no problem, right? They must have the same center. But we have to say that the coefficient can be determined by the function f of x. How? Look at here. You can see that. If you evaluate the case derivative at the center, okay, at the center, all right, you have only one term, and this term is equal to, k factorial ck. So that implies that ck can be determined by the case derivative of the function at z0. Okay? So once the complex function has been defined, in principle, you can compute the case derivatives, right, at z0, and from this formula you can recover the coefficient. Okay? So the coefficient is uniquely determined. Okay? So now you have two power series, all right? If you have two power series with the same center, And if they define the same analytic function, okay? If they define the same analytic function, then these two power series should be the same. Okay? They should be the same. So okay, so they are uniquely determined by Fz. Okay, this is the fact. So remark. Fz can now be written by n factorial is power, okay, and the C is in rho. So if a function can be given by a power series, then this power series actually can be written in this way. Okay. If Fz is given by a power series. So that's the situation. And the theorem, 15.3.3, termwise differentiation. Okay. The derived series of power series has the same OC. Okay, so we have shown already, right? So this is just a consequence. Because this theorem appears in the textbook. I just write it down. And theorem for termwise integration. The power series, okay, the power series summation Cn plus 1 obtained by termwise integration of a power series as the same OC original power series. Okay. Okay, so the idea actually it's well, you can apply the theorem, all right? Say that, or you can just directly compute the ROC, okay? And the way I get in my supplement is directly to compute the ROC of this new power series, okay? But you can do it from here. You can say that, well, it will define some analytical function, right? Right. But and then the derivative is equal to this one, right? It's very simple, right? But the question is that, well, how do you know that it can define a sensible analytic function? Because to define a sensible analytic function, you have to show like the ROC of this new power series, right? It's greater than 0, right? At least something. All right. So so to prevent such kind of argument, my approach is to, well, just compute the lim sup of the nth root of f's value of the coefficient. Okay. And you can see that it's just a practice of how to manipulate the lim sup computation. Okay, so please go through my proof. Okay, because it will illustrate some techniques. And it would be quite useful when you encounter a real problem. Okay, so now the next section is about, we want to know, to do something, to do the power series expansion of an analytic function. Why we study the power series expansion of an analytic function? Well, from the previous section, we know if we define a complex function by a power series, such a function is analytic. So the question is, are all analytic functions can be defined by power series, right? So that is quite natural, right? So we have some of, and here, the answer is that, well, we may not define an analytic function by a power series. Why? Because from our study, if an analytic function is defined by a power series, it is defined by only on a disk, right? It should be defined on a disk. Because outside the cross disk, it is undefined because it diverges. Okay? And we can encounter a lot of analytic function. The defining domain can be any open set. Not necessarily a disk, right? Not necessarily. So you can see that you have a discrepancy, right? At the beginning, you know that the answer is no. Right? The answer is no. That not every analytic function be defined by a power series. But there is one point that I will show to you that at least at local, any analytic function can be defined by a power series locally. Okay, locally. So let me draw the picture here, suppose that we have omega is any in a complex plane. Maybe you have hole here. Maybe you have some kind of hole or a cut here. Okay, so this is your open state. All right, so this is open state, and you have a function. All right, defined on this open state. So this is an open state. Okay, so omega is an open state. Okay. And you have a complex function defined on open state, which is analytic. Now, if that, then locally we can select a point here. All right, say this is 0. Then we can always define this function, okay? Locally, say that maybe we can, so we have, because it's open, right? So we can always find an open disk contained in the open state, right? And in this open disk, right, maybe we are able to define the function by a power series. And it's possible that we try to find its ROC as big as possible. Okay, as big as possible. But you can see that the biggest possible, because you have a hole here, so the biggest possible ROC should be from here to the boundary, right? To the boundary. Okay, and this region. So when F is defined on this open disk, we can define it by a power series. This is what we are going to do in this section. Okay, so it's impossible to define F on the omega by a power series. As you know, because omega is quite often not an open disk. So for here you have a hole, you have a cut, right? A lot of things. Yeah. But locally, you can define any analytic function by a power series locally. Okay? Alright, so this is our point. And well, the plane actually we have to use the Cauchy's integral formula. Alright, so it is quite lengthy. Okay, and so I decided not to cover it. I can't finish that. Only one page, okay, but it contains a lot of details. So let me just write down a theorem. Okay, and leave the detail for you to read. Okay, so now let me state it. An analytic function f of z. Okay? From an open state to Z. So here this is an open state. Okay? Right, so an analytic function is representable, right, by power series. In omega. That is for each open disk B Z0 R, okay, in omega, just like here, right? We have omega and we have a disk, right? So we have Z0 and R here, and it contained in the open set. There correspond, right? the power series expansion of f of z at z equal to z0. So f of z is equal to summation n equal to 0 to infinity fn z0 n factor z minus z power, which is just the Taylor series expansion of f of z about z equal to 0. Okay? So actually, this analytic function can be represented by a power series, and the coefficient actually is determined by f, because it is determined by the derivative of f at z0 of all orders. Okay? So this is uniquely defined. So once you have f, you know this quantity. So this power series is uniquely defined at every center z0. Okay, so that so you have you can have this, and the ROC of this power series actually is equal to the biggest radius, such that the disk is still contained in the open set. Okay, so for this case, that we will reach to the boundary of the hole here. So this is true for any z zone, any point on the open set. And as you know, at different z0, the coefficient may be different. Okay, right? You have different, because the coefficient depends on the derivative, length derivative at the point z0. So once the center changed, the power series, the representative power series will change. Okay, change. Any questions? Right. So the job is to prove the theorem. Actually, you have to prove that it has a ROC which is non-zero. Okay, for any such power series, you have to prove that. Okay, and so you need the Cauchy's integral formula. Okay, you need the Cauchy's formula to show that. Right. So so this is the property you have. So I want to emphasize again. The power series here, or you have a power series, suppose Z0 is here, then you will have R here, okay? So the power series at the Z0 here will be different from the power series given here, because the coefficient sequence are different. Okay, so you have to know that. Okay, you have to know that. But uniform convergence, actually, we start uniform convergence for real functions before, right? And so so it's a reading assignment. So I don't want quite similar to what we discussed before, and of course it contains more material than before. Okay, so please read this section. Okay, and so I will go forward to chapter 16 to talk about complex integration. Lorentz series. All right. We know Power series always defined on an open disk, right? But there are some useful representation of analytic functions. For example, sometimes we want to find a uniform an expression saying that with this we have a hole here. So sometimes we may want we may want to represent the analytic function around the hole by simple expression. Okay? And you know it is impossible to use a power series, right? Because a power series should have radius of a disk for absolute convergence, including the hole. But you know the hole here is something that we cannot define the function, right? It's square, we cannot define a function. So this is impossible. Okay, and so now we will see a kind of extension of the power series will give us a simple representation, right, for a function defined on this part. So it's called, and you can see this part is like an annulus, right? This is an annulus. Okay, so and such kind of representation is called the Lorentz series representation. Okay, so now here again, so now Lorentz series extension is an extension of the power series. So Z0 a fixed complex number. So it will be again used as a center. Okay, now we have Cn, but now the sequence is two-sided sequence. The index is from minus infinity to infinity. So it's a two-sided infinite sequence of complex numbers. Alright? Unlike the power series, for power series you have only one-sided infinite sequence, right? Starting n from 0 or starting from n to 1, that's fine, right? 0, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, etc. Okay. But to define a Lorentz series, you need a two-sided infinite sequence of complex numbers. Now, the two-sided infinite series of power functions summation n from minus infinity to infinity Cn v minus z0 to the nth power. So now the n can be negative. Okay? So it's two-sided infinite series or power series. And such a series is called a Lorentz series. Okay, so it's a Lorentz series with the center is 0. Okay, and the coefficients Cn. Okay, so you may regard a power series to be a special kind of Lorentz series, such that C sub n is equal to 0 for all n which are negative. Right? So this is a very special kind of Lorentz series. Right. So now, suppose we are given a Lorentz series. Okay, so n from minus infinity to infinity. Relate two things. Alpha is the lim sup, alright, of the nth root of the coefficient, absolute coefficient for n goes to infinity. So basically, we're talking about C sub n when n is positive. And the beta is the lim sup. N goes to infinity, but it's C minus n. Okay, so when the index goes to minus infinity, okay, so we have two limits to the sup to compute. Right, then the Lorentz series, okay, n from minus infinity to infinity, Cn v minus z0 nth power converges absolutely. Okay, absolutely. If beta is less than z minus z0, the distance of z to z0, 1 over alpha. Okay, so if the distance from the center is at least beta, but less than 1 over alpha, then this Lorentz series converges absolutely. And diverges. Right? Diverges. If either z minus z0 is less than beta, or z minus z0 is greater than 1 over alpha. Okay? So the situation is here. Okay? Wow. So in this region, the Lorentz series converge. Okay. But inside the small disk or outside the big disk, the Lorentz series diverge. But we don't have any conclusion about point on these two boundaries. Okay, we don't have that. All right, so this is the So range series, its convergent behavior is described by this figure. By this figure. And the proof is quite simple. Well, so fix C, okay, in the complex frame. So we just fix it. Okay. So we know n from 0 to infinity, Cn z minus z is 0, right? This one converges absolutely. Okay? If so n goes to infinity, right? And that diverges if so. Greater than 1. Right? The other thing is from minus 1 to minus infinity, Cn. Okay? So this one and so we can change this one to okay. So we can express that by this one, right? And this one converges absolutely if in so. C minus n, z minus z0 minus n absolute value is less than 1, then the diverges in so. Greater than 1. Okay? Now, the range series converge if and only if this part converge absolutely and this part converge absolutely, right? So they must be convergent so simultaneously. Either one diverge, then the whole thing diverges. Okay? The whole thing diverges. So this is the situation we have. Now look at the convergence part. This is if and only if the insert. Okay? 1 over, right? As before. Okay? How about this one? This is going to the insert. Okay, and n, c minus n, this one, right, is less than z minus z0. Okay? Because it's minus here, so not inverse, but it's this one. And this is going to limit, so n goes to infinity, and c minus n greater than 0. Now, this is equal to alpha, this is equal to beta. So now we can write down if all right, we have that, and if greater than beta diverges so that's combined together converges absolutely if and diverges if either or okay, so you have the conclusion there. So remark here is that if it's possible that alpha, the reciprocal of alpha is less than beta. If this is the case, then this is an empty set. Right? This is an empty set. Except at the center, because at the center, the zero, but zero you have something. So I think we were okay diverges everywhere. Here assuming that C so at least one negative term is non-zero. In this case, because when you put the zero there, then 0 is minus 1, minus 2 is undefined. So you have to know that. So if 1 over alpha is less than beta, then the Lorentz series diverges everywhere, okay, in the compass frame in C. Otherwise, you have this situation. Okay? So if beta is less than 1 over alpha, then you have an annulus in this region. All right, in this region, the Lorentz series converges absolutely. Okay, converges absolutely. So this is the situation we have. Okay, so now the region here will be denoted by the annulus will be denoted. The center is Z0, right? And beta is 1 over alpha. So presume beta is less than 1 over alpha. Okay? So we will denote this annulus by A at Z0, beta in the alpha, 1 over alpha. All right, a Lorentz series can be used to define a complex function. On the open annulus. So f of c okay, so as part series, any Lorentz series can be used by a complex function. And this complex function is well defined in this annulus. Okay, and this function, by using this Lorentz, it cannot be defined inside the small disk, and cannot be defined outside of the big disk. Okay. So you know as before. And now, this function, I define. Oh, okay. So, the microphone asked me to stop here. Okay. All right. So I will continue the discussion. And next week, next week would be the last week for this semester. So I hope to complete chapter 16, and so the final examination will include chapter 11, chapter 12, 13 up to 16. Okay. So the whole semester, okay, is accumulated, right? As I promised you at the beginning of the semester. So you have to prepare everything taught in this semester. All right. So I know you have a lot of things to read, and so if you have any comment to my supplements, let me know. If you think that I should cover more, let me know. Maybe I can revise my supplements to put more things. And it's very unfortunate. I mentioned that I suppose I can cover the analytic continuation, right? But I can't. It's time limitation. So I'm very sorry for that. I cannot cover analytic continuation. Okay. So see you next week.